Okay, so today I want to review the chapter 6 and chapter 11 of the Stat 5030 very quickly. So after that, we continue chapter 3. So chapter 3 of our textbook is about linear regression, but maybe you have different level of knowledge based on your past courses. So I would like to just make sure that everyone is comfortable to discuss linear regression. Okay, so I will share the screen and we start we continue chapter 6 of 5030 slides. Yeah. Okay. Yeah, first of all, I just want to make an announcement. So today is the January 23rd, and January the 30th, we have a seminar talk by a statistician. So the job candidate from the University of Pennsylvania will come to Wayne State, and I will discuss some stuff about the machine learning with the biomedical applications. And the seminar at I think the 2:45 p.m. to maybe the 3:45 to maybe 4 p.m. And also the February 6th, another statisticians, the former colleague, I forgot the name, but he's visiting campus for seminar talk, colloquium talk. That is also, I think, the 4:45. And he will be talking about non-parametric statistics. So these are good seminars to attend. So many of the mathematics department seminars are about more about the pure math, but these are statistics talks. So in the talks, usually, people don't really, figure out what exactly the speaker is talking about, but still, you can get some ideas and how, statistical research can go. Okay, so last time that we started the review of linear regression, and okay, so linear regression is this. So y is equal to a plus bx plus epsilon. So if we have n observations and if we use index I to represent observations, then we have yi is equal to a plus bxi plus epsilon. So at first, the observations are xi and yi. So these are observed values. And our objective is to estimate A and B. And epsilon is just the kind of the nuisance factor. So we cannot really observe, but always the error is there in statistical model. So basically, on the XY plane, we have data points, maybe 10 data points, 100 data points, in general, n observations. Then we want to fit the straight line a plus bx. So that is the objective of linear regression. Okay, so in terms of the probability theory, A and B are constants, and X is deterministic as well. Epsilon is random because it's an error, and Y is random because Y is function of epsilon. And the line, remember, that is determined so that the vertical distances, sum of squared vertical distances is minimized. So if we go horizontal, of course, the optimal line is different. So regressing y on x and regressing x on y becomes different line. So that means, for example, if we regress y on x, then that becomes y is equal to 2x. Then that does not mean that if we regress x on y, that becomes 1/2 times y. Actually, this does not happen. And A and B can be estimated in some way, but you can see that this function is quadratic function of x and A and B, quadratic function of A and B. So we can simply take the derivative with respect to A and derivative with respect to B to find the minimizer. And to observe that, an easy way is actually to use a matrix representation. And the matrix representation goes this way. So we have n observations, but we make a vector of all observations. So a vector of all observations of y. And for x, we prepare two columns. So first one is for intercept, so all ones. And the second column is x1 to xn, so all observations, so predictor values. Then if we define beta as this vector, this is 2 by 1 vector, and epsilon as vector of all error terms, then we can write the original equation as y is equal to x beta plus epsilon. So you can see that the y is, okay, so what's the dimension of y? Dimension of y is n by 1. Because we have, obviously n by 1. X, how about x? Dimension of x is, you can see, n by 2, right? And beta is 2 by 1. So you can see the product is n by 1. And epsilon, you can see, sorry, epsilon is n by 1 again. And actually the beta hat, that is estimate of A and B, beta hat is obtained by this formula, x prime x inverse x prime y. Okay, so beta hat is 2 by 1 vector. And actually this complicated right-hand side is also 2 by 1 vector. Why? Because, okay, so first x prime, this is x transpose. So that is what? X is n by 2. So x transpose is 2 by n. And x is again n by 2. So product is what? Product is 2 by 2 matrix. And we take the inverse. Inverse matrix is again 2 by 2. And x transpose, that is again 2 by n. Y is n by 1. So this is 2 by 1 matrix. So overall, this is 2 by 1. So beta hat is obtained in this way. So yeah, actually, this is very convenient. You can derive A hat and B hat separately by using some calculations, but actually this can be generalized for multiple linear regression in that the X has more columns. So actually this is the convenient form, and we should basically we should memorize this if you have studied applied statistics. And proof is pretty simple. So remember that we want to minimize the sum of epsilon squares. So I is equal to 1 to n epsilon I square. That is actually the epsilon transpose epsilon. This is 1 by n times n by 1. And this is actually the y minus x beta transpose times y minus x beta. So we want to minimize this quantity. So that is our objective function. So this is so-called sum of squares, or sum of squared residuals. And we want to solve this for beta, but the beta is a quadratic function. So you can differentiate this with respect to beta. Then actually that becomes 2 times x prime y minus x beta prime. So you can see that if you differentiate with respect to beta, basically that becomes x. So y minus x beta transposed x. And they use product rule. So this one also we differentiate, so negative x prime. So maybe I should say we have negative sign here. But anyway, so right hand side should be 0 because we minimize. So at minimizer, the derivative should be 0. Okay, so beta hat. So derivative should be 0. So if you solve this, then we can simply get beta hat is equal to x prime x inverse x prime y. So it just, you can solve this. You can expand this and move the, maybe divide by 2 first, then move x transpose y to the other side, then the multiply by this matrix, then beta hat becomes this. Okay. So x transpose x inverse x transpose y. Okay. So you can memorize it. Sometimes I ask proof in PhD qualifier in probability and statistics. I don't ask you proof in the exam, but that is the case. Yeah, so suppose that we consider the, yeah, I think this is from the previous example. So we have the square footage of condominiums and the prices of the condominiums. So we want to fit this line, and how to do that. And the price is response variable y, and the square footage is x. So here is the code. So we define the y as price and x as this matrix. This is, okay, we have 48 observations. So the matrix x is the vector of 1, actually 48 ones, and the x1 to x48. So this is x. So we repeat 148 times, and we use x as the predictor, so square footage as predictor. Then we can estimate this, the x transpose x inverse x transpose y. So transpose is t and solve is inverse, so you can get it. Then you can get a is this, so this is a hat, and this is b hat. So basically, the y is equal to negative 265 a hat, x, negative 265 plus 0.247 x, maybe plus epsilon. So this is our estimated equation. Yeah, so once we estimated this, we can calculate epsilon, right? So this is actually estimated value. So we write this as epsilon hat. Epsilon hat is equal to y plus 265 minus 0.247x. And in general, this is denoted as epsilon hat. So epsilon hat is represented by this. Or in matrix form, epsilon hat is this. Any questions so far? I think last time we covered almost these slides. And the beta hat is, the pair of a hat and b hat. So this has variability. So that means if we have the xy plane, suppose that the first data is, what happened? It sounds strange. I don't know, some errors. Or maybe we have to cancel this. So just, sorry. So suppose that the first data set is like this. Then we can make a straight line. So this is estimated line. Sorry, maybe. But if we observe another data set, maybe another data set is slightly different. So like this. Then for these observations, probably the fitted line is like this. So slightly different. So the A and B have some, variability. So A and B depends on X and Y is random. So that means A and B are also random. So A and B has some variability. So we can estimate the variability of the beta hat as well. Mathematically speaking, so beta hat is this quantity and Y is this quantity. So that means the beta hat is beta plus this term, and this term is random. So it depends on epsilon. So beta hat fluctuate. So A hat and B hat fluctuate. And we can estimate the variance of beta hat as the X transpose X inverse sigma square. Sigma square is the variance of error term. So the size of error for each observation. And variance of beta hat, actually this means 2x2 matrix which consists of these elements. So variance of A hat and variance of B hat, that is as usual. But here, the covariance between A hat and B hat. So covariance is a kind of the correlation with scale. So if covariance is positive, then A hat and B hat are positively correlated. So that means larger A is likely to imply larger B, and smaller A hat is likely to mean the smaller B hat. Yeah, so in general, if you estimate the straight line, then A and B are correlated. So for example, just to see this, the red line and the black line. Okay, so these are different both in slope and intercept. But you can see that so black one has smaller slope, right? But the larger intercept. But okay, so suppose that the data points are all around here. Then smaller slope means for example, we can write a line with even smaller slope. Then intercept tends to be larger, right? Because the most points are in the first quadrant. So that means if slope is smaller, then intercept should be larger. So that means the A and B are basically negatively correlated. So smaller slope mean larger intercept. So in this case, the variance of A hat and B hat, I mean the covariance of A hat and B hat, there should be negative. So beta hat, variance of beta hat has this information. Yeah, proof may be complicated, so I skip. Do you have any questions so far? Yeah, so this is pretty convenient. So X transpose is just the design matrix, the X we have defined. And just if we take the product of X transpose and X, then take inverse and multiply sigma square, then we got just the three information at the same time: variance of A, variance of B, and covariance of AB. To be exact, variance of A hat and variance of B hat and covariance of these two. Yeah, okay. So next, often we want to see how accurate A hat is or how accurate B hat is. And yes, so we have calculated how accurate the B hat is and A hat is by the variance of beta hat matrix. But what's the exact distribution of A hat? What's the exact distribution of B hat as well? Maybe possibly we can say what's the joint distribution of A hat and B hat. And actually this theorem gives just the distribution of A hat and B hat. So A hat is estimate for A. So A hat minus A is around 0. But we have some variation. So standard error of A hat is the size of the error. So this is just the square root of variance of A hat. And actually, if we take the ratio, okay, so it is standardized. So we expect that the mean is 0. Okay, so mean of TA hat is about, this is 0, we expect, and the variance of A hat, TA hat, so TA hat is around 1 if it's standardized, right? So, but what's the exact distribution? This is normal 0, 1 or another distribution. And actually this follows the T distribution with degrees of freedom n minus 2. So if n is 48 as in the previous example, then this is the T sub 46 distribution. So T distribution is almost the same distribution as normal distribution, but they slightly have heavier tails. Yeah, and the TB as well. So since we know the exact distribution of TA hat and the TB hat, that we can use it in a test. For example, we can test whether A is equal to 0 or whether or not A is equal to generally A sub 0 for some constant A naught. And the same for B. Usually people are not interested in the significance of A because intercept just, is an adjustment term. So it doesn't really matter much. And B is more important because the y is equal to the A plus bx plus epsilon. If B is 0, that means x is not associated with y. And B is positive, then x has positive association with y, right? So this is important because so sometimes to increase y, then we want to increase x, for example. So it's important to see if B is equal to B is significantly different from 0, and also B is either positive or negative. Those are important information. Questions so far? Yep. I think that these are covered, but just quickly I want to go over. And this is how to implement linear regression in R. So we can only we only have to use the LM function. Sorry, I think that this is the second slide of the R code. Probably we have to go back a few slides for the original code. So sorry, no code. I thought somewhere I wrote it, but oh yeah, here, sorry. Yeah. So to fit the regression model, just we can write the LM parenthesis y tilde x. So that is the format. So LM1 is the linear regression object. And the coefficient and the square footage is here. But now that we see a little more details of the output. Okay, so we get the summary of LM function. Then you can get some information. So this is the distribution of epsilon hat. So distribution of epsilon hat. And coefficient here. And you can see this is A hat, standard error of A hat. This is the variance of A hat square root. And this is for B hat, standard error of B hat. And this is T value, so the A minus A hat. Sorry, maybe the other way around. So A hat minus A hat minus 0, actually. A hat minus 0, so just A hat. Maybe I would say just A hat. A hat over standard error of A hat. And this is P value. So if we have distribution of this, so this is the T distribution with actually DEF 46 in this case, because we have 48 observations, and this variable follows T46 observations, T46 distribution. And this P value is basically the area of this, where this point is A hat over SE hat. Sorry, this is negative value, so maybe I should say that this is negative 3.109. So this is A hat over SEA, standard error of A hat. Yeah, so the area, total area is this, the P value. Yeah, so this is the linear regression. And yeah, so I will explain other things later. Yeah, I think almost this is what we want to discuss, but I would like to just briefly go over some of the next two sections slide. So at first, the fitted values. Fitted values is x beta hat, right? So originally the equation is y is equal to x beta plus epsilon, but the epsilon is error. So on average, that is 0. So what's the best guess for y, that is y hat? That is x times beta hat. Beta hat is our estimate for beta, and epsilon is, around 0. So the given x value, the estimated value of y is y hat, so x beta hat. And we can get this by using this fitted values function, or fitted of LM object, or LM bracket 5. Then we can get it. Yeah, so R basically determines the object based on the first few letters. So if you type LM1, for example, fitted, then probably you can get this object even without dot values. Maybe FITT returns the same thing, possibly. I don't know how many letters we need. That's the. Yeah, so these are fitted values. So Y1 hat, Y2 hat, and so on. Y48 hat. So estimated price for each condominium. So first one is $384,000 and so on. And these are, okay, so omitted, but it returns the same object. And also residuals, you can see residuals is the epsilon hat, and it's obtained by LM1 $ residuals, or resid LM1, or LM1 bracket 2. Yeah, I think that's almost everything I want to discuss. Okay, so this is the residual plot. So remember that, okay, so this is epsilon hat and this is x. And you can see that this is the line of 0. And you can see whether or not epsilon hat has some pattern. If epsilon hat has some pattern, then that means that we can extract more information from somewhere to explain why. So in this case, maybe one noticeable thing is the observations are larger in absolute value. Okay. So these observations are larger in absolute value compared to these observations. So that is one thing. So probably the variance is not equal. Probably we need some transformation of x, or maybe both x and y. And the second one is maybe some cluster here. So many observations are negative here. So maybe these are potential problem to fit a linear model, but at least just I want to say that the residual plot, x versus epsilon hat, gives us some information about whether or not linear model fits well for the data. Yeah, I think that is all we want. Oh, maybe another one, maybe. Yeah. And this is the plot, or basically to represent the distribution of epsilon hat. So epsilon are normal random variables. So if we order epsilon hat in increasing order, then we consider theoretical quantile points on x-axis and the quantile points on the y-axis. Theoretical distribution of epsilon, then it should have the straight line pattern, diagonal straight line pattern. So we should have y is equal to x. So if these observations are so deviated from this straight line, then we have some violation of distribution of epsilon. So usually we assume that epsilon is normal 0, 1, but if all points are not on a straight line, then it violates the assumption of normal random variables, normality of epsilon. And actually maybe some curvature here, that may be a problem, and maybe we need some transformation of, I don't know, that maybe we can add some predictors to make these errors smaller, or these errors move above, or epsilon hat larger. So probably we need a transformation of y to solve this issue. Yeah, but the point is that if we compare the so if we compare the theoretical distribution of epsilon and the distribution of epsilon hat, then we can see if normality assumption is satisfied or not. So I think these are, these are basically what we want to discuss in chapter 6.2. And chapter 6.3 discusses the prediction interval and the confidence intervals. How many of you have heard of confidence interval? I think that I expect all. No? How many of you have not heard of confidence interval before? I think confidence interval is covered in any statistics course, even at 2000 level. So basic idea is that we have the true parameter, okay? But based on data that we make our interval guess on this beta. So this is the interval estimation of beta. And if we have different data set, we have different interval guess. Sometimes it misses true beta. But if, for example, 80% of intervals, I think a method to construct confidence interval guarantees that 80% of confidence intervals cover true parameter beta, then we call that method as 80% confidence interval. So that is the confidence interval. And how many of you have heard of prediction interval? Prediction interval, 1, 2, Victoria, Bill, okay, not many. Yeah, Tauhid, yes. So prediction interval is actually the range for which y falls into. So maybe we can explain this as this with this graph. Okay, so the black circles are observations, and the black line is the true. Actually, not true, but this is fitted line. This is fitted line, okay. And the red ones are red pair of line is confidence interval, and green pair of lines is prediction interval. So red lines represents where this true parameter falls in. So in this case, the true parameter represents a straight line. So that means the true regression line should be within the two red dotted line. So for example, the so line becomes this, or a line becomes this, or something, but all are estimate for the true regression line, but the true regression line is within this band with 95% probability. So you can see that so we have different data sets of the same size, then we have different straight line, but you can imagine that so we have the true line, but the true line is probably in between these two, the red dotted line. So so that is what this red the dotted curves means. You can see that this curve have some curvature, right? Because if slope is larger, then around here, actually the line is at a lower position, and around here higher position. And if the line moves around our estimate, then it makes some band, and the band is narrower around here, but wider around here. So when line moves, then the area that the line goes through becomes actually the hyperbola. So that's why these two lines are not very straight lines, but actually the two curves. And the green green dotted curves represents 95% coverage of data points. So if you observe for example, 100 new observations from the same phenomenon, then 95% of observations should be within these green intervals. Actually, in this case, 48 observations and only two observations are out of this band, probably. This is almost boundary, but that's probably 2. And you can see 2 out of 48 is around 5%. So this is the existing observations. But basically, if linear model is correct, then 95% of observations are within this band. So this is prediction band. So confidence band is the band for truth, so true line. Prediction bands or prediction intervals are bands for observations. Maybe in short, we can say red curves for black line and the green curves for black circles. Yeah. And correlation coefficient, probably you don't really need much explanation to correlation, but the correlation coefficient is, I think, yeah, correlation coefficient is defined by, so this quantity. So covariance divided by square root of variance times square root of variance, or we can say this. So correlation basically describes the linear, so how strongly X and Y are linearly correlated. So yeah, you can see this graph. So if X and Y, okay, so nothing is written, but suppose we have X axis and Y axis, then X and Y are not linearly related. So correlation is 0. If negatively related, then the correlation is negative. Here again, negatively correlated, correlation is negative. And if the relationship is stronger, then correlation coefficient approaches to -1. And a positive correlation, that's the same thing. So positive correlation, larger X means larger Y, then correlation coefficient is positive. Then yeah, if correlation is, relationship is strong, then it is close to 1. And the correlation isn't equal to the slope. As long as X and Y has perfect relationship, the always correlation is 1, even if so it does not matter that this line is Y is equal to X or Y is equal to 0.2X. It doesn't matter. If perfect relationship, no noise, then correlation is 1. -1 as well. Correlation of 0 does not mean X and Y is not related, because in this case, no linear relationship, no linear trend line, or maybe just flat linear trend line, but still X and Y may be related. But this just means larger X neither mean larger Y nor smaller Y. All of these cases. Some pattern, but the X and Y do not have a linear relationship. A larger X does not imply larger Y, and does not imply smaller Y either. Yeah. Yeah, so correlation is basically calculated once you observed the observations, then correlation is calculated as basically the summation of this xi minus x bar times yi minus y bar. And that's why if xi and yi are larger at the same time, then more points here and here, that makes this product positive. So that makes correlation positive. So that's why we can quantify the linear relationship by this quantity. And to be exact, the correlation for observations are calculated by this way. This divided by standard deviation of x times standard deviation of y. And correlation, how correlation and the slope of the linear regression line is related. So I think the many people are confused if they are from other than statistics. A few years ago, I found that the famous economists, they mixed up correlation and the slope of linear regression. So slope of linear regression, B hat, is equal to correlation times Sy over Sx. Okay, so in some sense, beta hat and R are similar quantity. S sub y is standard deviation of y. This is a scale of y. So this is scale of x. So after we adjust scale of x and the scale of y, then R and B are the same. Okay. So it's a kind of, yeah.
Is S of x and S of y the sample standard or the population
sample standard deviation? Yes. So
okay,
S sub x, sample standard deviation. Yeah, this, S sub y over S sub x is a kind of clear, so these quantities are here for a clear reason. So think about y is someone's height in meter and x is someone's weight in kilogram. Okay, so but we just changed the y as height in centimeter. That means the yi becomes 100 times larger. 2 meter is 200 centimeter. So twice, 100 times larger. So in such a case, of course, the slope as well as intercept becomes 100 times larger. Right? So if scale of y becomes 100 times larger, then certainly b hat becomes 100 times larger. So both should become 100 times larger. So the other way around is also true. X is reported in gram, then X is 1,000 times larger. That makes slope just 1,000th of the original size. So we have to divide this by S sub x. Yeah, if X and Y are standardized, B hat is R hat. So that's the chapter 6. Do you have any questions about the linear regression? Okay, if not, we go to chapter 11. So chapter 11 is multiple linear regression. Maybe yes. So we have multiple observations. So multiple variables, multiple predictors, sorry. So last time that we want to explain the price, this is a different data set from chapter 6, but the price is explained by square footage in the last chapter. But here we introduce more variables, the year built and the number of bedrooms and the number of bathrooms. So these 4 variables are all related to price, and probably these are all used to estimate the price. And so we want to explain price by the other 4 factors: square footage, year, bedroom, and bathroom. So that is what we want to do. And okay, so this graph is actually created by just simple code, the pairs of data frame. So D2 is a data frame with these 5 variables. So maybe it has maybe, I don't know how many observations, maybe 200 observations. So we have 200 by 5 in general, n by 5 matrix. And just we put matrix in this pairs function, then we get pairwise plot. We can also calculate correlation between variables. Price and the square footage, okay, the correlation is 0.8985, but also price and the year, price and the bedroom, price and the bathroom, all positive. Date, this is strange. Usually, the later date price is higher, but this is actually data from around the financial crisis. So actually the later years price is lower, but anyway. So we can get the correlation plot. And the correlation can be represented by this kind of scatter plot. So you can see, price and price has correlation of 1. So that is obvious. So these are all 1. So you can see 1. But also the square footage and the price have high correlation. So the thicker color, thicker blue. But the number of bedrooms and the price have, smaller correlation. So here, blue. And actually, if the correlation is less than 0, then these are red. These are red. And that can be obtained by the correlation plot of the correlation object. So correlation of this 6 by 6 matrix. So you can just put it in correlation CORR plot. But this is in the CORR plot library. So you have to import this library first. Yeah, so these are maybe some good, the code to represent the data, to describe the data. And sometimes we want to describe all predictors versus just a response variable so that we don't have to present all pair of, scatter plots. So, for example, if we want to explain price by these 4 factors, maybe you don't really care how square footage is related to year, right? So it may give some information, but if our objective is to estimate price, then that is good. So yeah, so this is the relationship between price and each of the predictors. So price and date, you can see slight positive, slightly negative slope here. Maybe not this slash, like this. And here, positive relationship. Here, positive, probably nonlinear relationship, maybe. Here, it's not clear, and like this. And here, maybe overall positive relationship. Sometimes we want to compare 2 discrete variables, number of bedroom and number of bathroom. If you create the plot, then probably it gives you no information. Number of bedrooms, number of bathrooms, then plot is like this. So for example, the many houses may have 4 bedrooms and 2 bathrooms, but since all plots are on the same place, we cannot really distinguish those 2 observations. So then as a result, we will get the meaningless graph. So we add some noise so that we know that many observations are here. So 4 bedrooms and 2 bathrooms, but we add artificial noise so that this is sometimes 4.1, 3.9, and this is sometimes 1.9 and 2.1, so that we can see there are many observations here. Obviously, we can see more observation here than this one. So this is jitter plot. So you can use the jitter function to make a plot. So I discussed these figures just for your final presentations. maybe these are useful. And multiple linear regression. So in general, if we have more variables, that we have this linear model. So you can see this is linear with respect to beta naught to beta p. So we have more predictors here. In chapter 6, we only have x, so x1, I would say. But here we have x1 to xp. Yeah, but anyway, so the methodology is similar. We just minimize the sum of squared distance, vertical distance. I mean the distance in the direction of y. And yeah, we have the similar matrix representation, and matrix actually once you set up matrices, then the model is exactly the same as the simple linear regression with one predictor. And again, we want to minimize this quantity, that is this quantity, and the beta hat is obtained in the same formula. And you can define variance of beta hat in a similar way. Yeah, so that is chapter 11. You can see more details if you would like to review more. Maybe we discuss the one figure at last. Yeah, so we want to check if epsilon hat are all random. Epsilon 1 hat to epsilon n hat are all random. So to verify that, the recommended method is each of the predictor x1, x2, x3, x4. So these are actually different data set from the housing price data set, but each of the predictor variables and epsilon hat, that is the recommended method. And this should have random pattern. So this is 0, this is 0, this is 0, this is 0. So in this case, it's pretty good. So all observations are at random. So no curvature or no increasing variance. We don't have that kind of features. So the observations are, I would say, epsilon hats are all random. So if you do multiple linear regression, then I recommend you to make this figure. Or even other more complicated machine learning models. This is a recommended method. Do you have any questions? Yeah, in 50-30, probably I spend maybe 5 lectures to cover, but here only less than 1 hour. Okay, so now do you have any questions about linear regression? Just this is a quick review, and I think review is good for everyone, right? Yeah, so math professor seems to have the perfect knowledge in calculus, but that does not mean they studied calculus perfectly when they are in high school. But they teach calculus 10 times, so of course they know everything. So it's good that you review it, then you can make that knowledge more solid. Okay, so now we go to chapter 3 of this 5820 slides. So just I want to explain what I haven't discussed in the 5030 slides. Okay, so here is the output of LM function. So, okay, so originally we have the sales amount, and the sales depends on the advertising spending on TV and radio and the newspaper. And newspaper sounds the little effect on sales. So here that we decided to regress sales. Sales is Y on TV, X1, I should say, and the square of TV, X2, and the radio, X3. To put square, we have to write the ITV square. Because actually the TV square usually works. outside of LM function, but the inside LM function, the product of two variables have different meaning. So in general, x1 times x2 means x1 and x2 and x1 times x2. So sometimes we have different meanings. So that's why we have to put I here to include square of TV. And then radio, this is x3. Then this is the result. So y is equal to intercept plus this 7.8. So this is 0.078 times x1 TV, and negative maybe 0.000113 times TV square, and the 0.193 times x3. So that is the obtained result. And you can see that all p-values are very small. So that means that we reject null hypothesis that these estimates are actually the true parameters are actually 0. So that means true parameters are not equal to 0 in this result. So this means this. So sales is this plus this times TV and this times TV square plus this times radio and plus error. Generally, we write in this way, as we have seen in chapter 11. So here we have 3 predictors. So we say P is equal to 3. We have 200 observations. So we say N is equal to 200 sample size. Then X1, X2, X3. And residuals, we have 200 residuals. And this is the summary statistics for residuals. So minimum residual is negative 7.38. Maximum residual is 3.57. So it's actually asymmetric. So minimum is very small. Maximum somewhat large. First quartile, 25th percentile, and median and third quartile. So you can see that some observations are very, some epsilon hat are very small. So that is the what this indicates. And actually histogram is here. So we have 2 kind of outliers. These are, yeah, are kind of almost symmetric, but these 2 are maybe outliers. Yeah, so here I would like to explain some other output. So you can see in LM output that we have the residual standard error below estimation results. And that is 1.517 on 196 degrees of freedom. So that means the sigma hat. Sigma hat is the variance of epsilon. So estimate for sigma hat is 1.517. And the 196 is degrees of freedom. So this is actually 200 minus 4. And 4 is the number of parameters in the, number of coefficients in the linear model. We have intercept, TV square, and radio. So intercept, TV square, and radio. So we have 4 parameters. So 200 minus 4 is degrees of freedom. This will be used to calculate some other distribution of the statistics. And the sigma hat is calculated by this formula. So this is somewhat reasonable because this summation is summation of epsilon I hat square. I is equal to 1 to 200 in this case. And as a common sense, we want to calculate just the variance. So that is the average of epsilon I hat square. So 1 over 200. That is rough idea. But here we have -1, p -1. So the idea is that the beta naught, beta 1, beta p are estimated in this model. So that makes the epsilon I hat slightly smaller than epsilon I itself. So actually, if we use this formula, it underestimates the sigma hat. So that's why we subtract some numbers to make it expectation of ips sigma hat square equal to sigma square. So to make this property, to have this property, that we have to subtract p and 1. So here p is 3. P is 3, right? So in TV and the TV square and the residual, so P is equal to 3. If we include the intercept, actually that is P plus 1. Yeah, and epsilon hat over sigma hat follows T distribution with degrees of freedom 196. So that's why it reports 196 here. Do you have questions? How many people are here? Yep. Okay. Oh, I think the last time that someone asked me to check attendance, right? Yeah, so I recommend always to attend all lecture unless special reasons. Okay, so Victoria here. And
yes.
Yeah, okay, so Nick,
I'm here.
Nicholas, right? Nicholas and Michael. I think I have to check in some way. And yeah, okay, so Michael here, Luke here, and Erica here, Bill here, and James. James have taken the 6840, right? I think many students come from the 6840. Hunter, okay, great.
Yeah, I'm here.
Yeah, Michael, Luke, okay, Luke.
Yeah.
Yeah, here, yeah, I don't know. Yes. Okay, so now we go to the next section. Not next section, yeah. Yeah, and just one remark. So, for example, to make a QQ plot or X versus residuals, we use epsilon hat because we don't know epsilon. But epsilon and epsilon hat have different distributions. Yeah, actually, epsilon follows basically T distribution, right? Divided by sigma square hat, so T distribution. So we check the QQ plot and we expect that the QQ plot are on a straight line. So the observations are on a straight line in QQ plot. But actually, that is if we use epsilon. But if we use epsilon hat, that is slightly different. So probably just slightly, we have some curvature probably. Yep. So epsilon and epsilon hat are different. Even in statistical theory, sometimes the difference is ignored. Sometimes we care about it, but in some cases it's too complicated. But the epsilon hat actually follows T distribution. So actually slight heavier tail. So epsilon hat, distribution of epsilon hat has slightly heavier tails than distribution of epsilon. Yeah, here the T distribution, several T distribution with different degrees of freedom. So orange one T distribution with DF1, purple one degree 2, the blue one degree 5, and the black one is degree infinity, and the degree infinity is actually the same as normal 0, 1. And you can see, so these tail parts are different. But as degrees of freedom gets larger, it approaches to black one quickly. So in this data example, we have degrees of freedom of 196. So usually the degrees of freedom larger than maybe 50, that is almost the same as normal distribution.
50 or 15? 50 or
50,
15?
50. I would say 50. So this is just a ballpark estimate, but a 50, 50, we cannot almost distinguish those. 15, yeah, maybe we can distinguish it, but yeah, but still the difference is small. I would say 50, 50, or 30, 30. And the next line of LM output is multiple R squared and adjusted R squared. So these are similar number, 0.9167, 0.9154. And the multiple R squared basically expresses the okay, so this represents the what percentages of variability in Y is explained by predictors. So I would say that, okay, so suppose that we have x-axis and y-axis. And we have 5 observations here. Okay, so this is simplest case. And this has, of course, variability in Y. So one observation here, one here, one here, one here, one here. So we have variability of Y here. But once you fit the regression line, okay, so this is X, and we fit the regression line here. Error is almost 0. Okay, so error is almost 0. Maybe slightly, maybe slight error here and slight error here, slight error here, but error is almost 0. So variance of Y and the estimated variance of Y and the estimated variance of epsilon square, epsilon. So this ratio is this one. So multiple R square means the percentage which is explained by this regression line. So that is multiple R squared. So that means, roughly speaking, we can say that the 91.67% of variability in Y is explained by X. So that is maybe X1 to X3. So that is the meaning of multiple R squared. Yeah, if you don't really fully agree to my, the statement, then you can say that is the, definition of my sentence. Okay, so the 91.67% of the variation in Y is explained by the predictors X1 to X3. So that sentence, the exact meaning of that sentence is this: multiple R squared is 0.9167. Yep. And adjusted R squared, it's similar quantity, but we have some adjustment term. So we have the P here. So that means the error size is inflated a little bit, because if we just divide by n-1, then that's actually smaller. The entire numerator is smaller. But if we have P, entire numerator is larger. So this is inflated. So that basically means that if P is larger, it's penalized. Sorry. Just a moment, please. I think I accidentally closed this. Yep. Yeah, sorry, the P penalize the R square. So large P, so the large P is penalized in adjusted R square. Because P is large, then adjusted R square is small. So P large. Adjusted R square small. So this is a kind of reasonable, because if we have more predictors, we can explain more. So if we don't, if P is not involved, this may not be, fair comparison of models with different P's. So it's a kind of, it kind of penalizes the P when we calculate adjusted R square. And a little more exact meaning is that if X is not relevant to Y, then expected value of numerator is 1. And also expected value of the denominator is also 1. So 1/1 is 1. So adjusted R square is around 0 if X and Y are not related. So that is the meaning of adjusted R square. So suppose we have N is, suppose N is 200 and we introduce many predictors, maybe 50 predictors. Then just accidentally, X explain Y somewhat. But still adjusted R square is around 0 because large P is penalized. Yeah, and actually this sentence isn't entirely correct. The expectation of the adjusted R square is always 0 when all predictors don't have any true relationship with Y. But actually the expectation is separated for numerator and the denominator. So each of the expectation is 1. So adjusted R square is around 0, but in general, expectation of A over B isn't equal to expectation of A over expectation of B. So this sentence isn't mathematically correct, but as an intuition, so this is close to the true description. Yeah. So R square is the percentage. So multiple R square is the percentage of variation explained. So that is between 0 and 1. I mean the ratio. So between 0 and 1. But adjusted R square sometimes gets negative because that's around 0 if the X and Y are not related. Do you have any questions? I think 3.A only. Oh, okay, still have many. Yeah, and here it explains the relationship between correlation coefficient. Correlation coefficient, usually we use R, and the parameter version, the R is estimate, and the parameter is usually rho. And what's the the relationship between R and capital R square, sorry, the capital R square and R. Correlation is higher than observation is like this. So that means that mostly X explains Y. So larger correlation coefficient R means larger R square. So R and capital R square are kind of related. And actually we have relationship, and the square of correlation coefficient is exactly equal to multiple R square. Yeah, we can use some algebra to show it, but maybe just I want to explain that. So that's why we say that is R square. But adjusted version, of course, it's different. Yeah, sorry. So this is true if only one X. More than one X, we cannot really define correlation coefficient between Y and multiple X. So if only one X, simple linear regression, XY, then R square, multiple R square is equal to square of correlation. Yeah, so that is what we want to discuss today. So next time we continue chapter 3. I think probably we may not have a quiz question for today because we reviewed chapter 6 and 11. Yeah, maybe one quiz, but yeah, I will double check. Do you have any questions?